Hi, I want to use this old presentation of mine to explain TAD, the Architect's Desktop. This particular presentation is actually so old that it is I did not even have this. Let me just try and hide this particular window. Okay, sorry about that. So it did not even have the word BIM those days. This is I think somewhere around 2002 or so. Now, what is the context which TAD is addressing? TAD addresses the situation where an architect finds himself in all kinds of mess, right from very early stage where he's confused about what he needs to design. He's got various kinds of imaginations coming up, popping up. They are not really fully organized, and then they are put together, and then they are further put together, and then the building is made, and then later on the building is used, and then maybe somebody goes and makes an extension to that building, as you can see here. So architecture is all of that. Architecture is not just that part where you more or less finalize your design and that's what the design is, but actually architecture is all of this. Now, so you need a model which will help you kind of manage this reality which we are in, and that model has to be holistic, and we need to have a capability to look at the model from various different views. Because if you were to re-represent the model again and again, the way it happens today in CAD software, like when we design, we use one software. When we want to visualize, we use another software. When we want to find out the energy calculations, we use a third software. Then it all creates a mess because the re-representation can lead to errors. Uh, then the other thing which we need is that we need to respect design cycles. Architects do not really think linearly. We think cyclically. We work over a design, and then like a potter at work, we walk through the same design again, refining it along the way. Then we walk over the design again and again. Each time you are actually touching all the parts of the design. So sometimes you are throwing away information which is not really of much use to you, but then you also have information which are quite relevant. The truth is that through all those design cycles, you still have to communicate between all the members of your staff and other consultants who are involved in that design. They say that if you were to describe any complex problem very accurately, then the solution is just one step away. It's just 1% of the effort. And I found that if you were to have a BIM system which actually handles all this, then it's very important to talk about what is that representation? What is that representation? What is that description which you're going to give for your design? And remember, the design is actually presenting itself in all kinds of ways. In the initial stages, they are just quite hazy and sketchy and bubble diagrams. You don't even know the shape of the rooms. You don't even know the shape of the building. Nothing. And then it goes all the way to an actual building. So there's a lot of complex things going on there, and that particular description should be respect the complexity which is out there. Now, if you ask each architect, how do they go about actually designing? Each one would have their own way to model their problem. Each one is like the six blind men in the elephant story. Each person is blind in his or her own way, and yet they are able to kind of create some kind of a model on which they will then peg their design process on, and then they will kind of use that model to interrogate their design process as they move along. All of them are quite nice, nothing wrong particularly in each of these particular design mind models which people carry in their heads. However, we must remember that the rest of the people in that office would be able to understand you only if they understand the mental model with which you are designing. So this becomes a big problem if you're talking about a central communication system. My answer to that is that we should have a kind of a super model, kind of a model which subsumes all the other modeling systems, just so that each of the interpretations can still happen, but yet at the same time, at a very high level, all these mind models are actually subsets of one universal model. Now, this is not really very strange as it may look. Take the concept of a human being. There's this overarching model about a human being that there's a head and there's a neck and there are hands and whatnot, torso, legs, all that. That doesn't mean that there are no individual variations in that model. Each individual is actually very as different as anybody else. Nobody is the same, but yet all of us will fit into one super mind model. Now, can CAD models be suitable in such a situation? Well, CAD models are useful. It does have a picture in front of you, and a picture does speak a million words, but it's actually talking about only the visual aspect. And if you start putting in a lot of stuff into that CAD model, it'll quickly start becoming extremely resource hungry. If you say take a regular 3D software and somehow the other manage to squeeze in some non-visual information into that 3D software, you'll find that it is really resource hungry. So what we really need is not just arbitrarily put in a lot of stuff into a CAD model and say that is BIM, but what we need is a much more deeper understanding and a much more cleverer understanding to handle the resource requirements. So you take a CAD program which will look at a tube with a hole in the side. So you can see the hole in the side here, and I've deliberately made a kind of a mesh to look at that tube. The next slide, you'll see it in proper solid view. And we need to know uh, what happened to this wall thickness. Did we actually expand the outer what do you say cylinder, or did we work on the inner cylinder? On what basis was the thickness established? Now this is a very important question. You may think that it is not so, and now when you have a hole inside that, you have even more complex problems. So you have a lot of logical questions when you talk about designs, where you need to talk about both the built matter as well as the spaces. In architecture is one odd subject as far as the ingredients which the subject needs to tackle. It's got this figure ground confusion. Like this is a famous figure ground confusion. If you concentrate on the two faces, that's all what you would see. But if you concentrate on the central image over there, you will see a chalice or a vase, whatever you may want to call it. And the thing is that architects are continuously dealing with this paradoxical figure ground situation. On one hand, what is important is the space, but then space cannot be created without the walls. So then you focus your attention on the walls, but then later on you realize that you need to focus back on the space, and it keeps flitting between the space and the wall and the space and the wall. What I mean by space and wall is covering a lot of things. When I say wall, it means a lot of built matter around you. And when I talk about space, there's only one space, which is universal space, and many times, unfortunately, it's forgotten. But the space is where we all exist and we all live. We are not like termites. We live in who live in inside the walls. We are people who live in spaces, and we need to worry about how that life happens there. So how do you get a solution to this figure ground confusion? Now, let me pause here for a minute, and it's not explained in this slide, but let me pause here and tell you about uh, subjects which do have the same figure ground confusion. Take music, for example. Music talks about the notes which a musician would play, but also it talks about the silences between the notes, and both are equally important. You can't say there's a silence have to be ignored and you just worry about the notes. That's not going to work out. You can't play that particular piece of music if somebody writes it down like that. You need to know when the pauses happen, when the silence happens. So the silence is equivalent to the space, and the notes themselves are equivalent to the built matter. And these guys, the musical people, the musicians, they solve this problem completely. They address this particular problem, and their music notation system talks both about the what needs to be played and also about the silences. And if both were not represented, you would not have been in a position to play back musical compositions by long forgotten and dead musicians like Beethoven and Bach and Mozart and whoever. So what I'm talking here is that I realize that we need a new representation system, which is not really out there in the world, which talks about figure and ground in the same way. Now, what I realized that there is a way out to solve this, because it's quite tough if you were to handle this paradox that if you talk about the faces, then you can't talk about the vase, and then if you talk about the vase, then you can't talk about the faces. If you want to talk about both of them, usually would need to have some kind of redundancy. What I realized is that we can actually represent everything as spaces. After all, take a brick, for example. You hold that brick in front of you, and you will see a rectangular cuboid, and you can imagine at one point in time that rectangular cuboid was a piece of space into which the material of the brick could be poured into. So everything is actually a space, including the built matter. And that gave me a clue, and that is how the underlying principle of TAD evolved. So the same tube, I would now look at it once again, and instead of looking at it as a tube, I will say that let me look at that overall cylinder, outside cylinder, as one cylinder, which I call as envelope, the inside hole as the atom, and the particular hole on the side between the atom and the envelope is known as a connector. So you can actually describe that same tube, but this time described with three different parts, three different spaces. So let's see how traditional CAD actually addresses this. It actually doesn't address it. It just traces over, as you can see here in this animation, over what you believe to be the edge of the wall in a room, in a small room. So here it is, I've drawn this and I've shaded that. And what the CAD did is that it drew the wall and it emphasized that particular yellow area over there. And it left it to me for me to understand what the spaces are. The spaces are actually not there inside that CAD program at all. So, but how did TAD handle this? In TAD, we talk about the outer envelope, and then we say there's an inside atom, and inside that atom there's a connector, and there you are. I have represented that particular room. Now, inside that room, I further put in an artifact, say a table, and if you look closely at that artifact, voila, it looks like this. And that by itself is actually a collection of atoms envelopes. In this case, there's no real connector, but you could have connectors here. Suppose there was a hole on the side here, and then what will happen is that you have actually repeated the same classification once again. So the room started with atoms, envelopes, and connector, and the table in the room also started with atom, envelope, and connector. If you were to have inside this table a drawer, and that drawer itself would be atoms, envelope, and connector, and if you put a small stapler inside that, or a pencil sharpener over there, that pencil sharpener also will have atom, envelope, and connector, and it goes all the way in fractally. And this is what gives a TAD a major advantage, because it can actually talk about all kinds of architectural elements. In fact, it can talk about all of built environment, irrespective of whether it's architecture. You could probably even design a car like this if you had enough geometric modeling capability, but that's for later. This particular diagram actually goes through the entire classification, which I discovered that it's there in architecture, and this is what is coded into TAD. So what I claim is that all of architecture contains spaces and solids. Spaces itself contains atoms, envelopes, and connectors, which I just explained, and the outer envelope could contain 1 to n number of atoms. Okay, it can also contain 1 to n number of connectors. The connector could connect another connector by itself, or it could connect other atoms, and it could connect between atoms and envelopes. Okay, so that's what's happening with space. And now when you look at built matter, which is the first thing is known as an artifact, and the other, what is left over between atoms, envelopes, and connectors is known as a leftover. But leftover itself could have artifacts, and there's something called link nodes, which represents things like electrical wiring and plumbing and things like that, which are actually connected to each other. And this artifact, if you take a look at it, is actually fractally going back into being atoms, envelopes, and connectors. And once again, you will have leftovers, and in that leftover, once again, you have artifacts, and then those artifacts, strangely enough, is once again atoms, envelopes, and connectors, and then after the Boolean subtraction between them, you again get leftovers, and it goes on and on and on and on, and thereby describes the entire building. So the SFA classification system, or the taxonomy, can model all the way from a hinge to all the way to a city, maybe the entire universe if you really want. There was this curious article which I read in Business Week 2001. That was around the time when I had made this particular presentation also. And here is what that author was claiming: clever mathematical techniques are the foundation of increasingly realistic computer models and simulations. Now, math research is on the verge of creating tools that mathematicians hope will cut two ways, help scientists unlock explanations to many phenomena that remain mysterious, and produce new modeling systems. And also, the second one is to produce a new modeling system that would revolutionize product development and manufacturing. All this could be coming from fractals, those crinkly looking lines that look the same no matter how much they are magnified. So that is actually one of the fractal system which is used to talk about buildings. In TAD Designer, the system actually keeps track or allows the architect to keep track of the design through all those stages which I explained to you. And each cycle can be represented and queried logically. So this design cycle and iterations actually allow you to really knock off pencils. You don't have to be using pencils to show your haziness. You can be hazy to begin with using TAD and then end up with a final product later on. So after that, each of these logical units which gets placed inside this TAD representation can separately be enriched. You can talk about its cost, you can talk about who manufactures it, who's the supplier, what are the physical properties, what is the specific heat, what is the acoustic absorption coefficient on that, and what have you. Everything can be put into it. And this is another major advantage which TAD has, that it allows all kinds of enrichments to happen to each of those logical units inside TAD. Now, let me look at it from another angle, and which is that software programming is usually written in a silo where there's a team of programmers, there's a system analyst, and there's the user. And the system analyst goes over to the user, that's the designer or the architect in this case, and asks that particular person, okay, what all things do you need? And he'll come back to the software company saying that I need 1, 2, 3, 4, 5. But it turns out that particular designer forgot to give these two feedback, which came in later, and then that creates a hiccup. So the system analyst goes back to that architect, finds out what more needs to be done, comes back, recodes it, and it goes on and on like that between the company and the designer. And it turns out that you have revision after revision after revision of all these kind of design softwares. But that's not how I'm envisaging TAD. I'm quite glad that this model of envisaging TAD is still valid, though it's been quite some years since I made this particular presentation. So TAD also would have a development team, and TAD would incorporate some of the features. But some of the features like ABCD actually came from the users themselves, and they get plugged into TAD seamlessly, even though there's no real programming. And this is the way by which many other software also works. It's not something which purely unique to TAD. So you have customizable scripts which enhance the capability of a lot of your software, including a browser which you use. It's got something known as extensions, and you can add Chrome extensions, for example, and improve the functionality of your browser. So that's a pretty standard approach nowadays. You don't have to go around rebuilding or remaking that software and new version of the software. Of course, new versions would come up, but they will be a lot lesser. And in between, the community would also contribute to a lot of the additional requirements which TAD would need. So that's what those days my company was called Tangent Software, and that's the company would have done it. But now Tangent Software is no longer there, and I'm now working under a different company, and same TAD only. And then you can do all these kind of things like using power modeling. You can add in simulations. You can talk about heat calculations and so on. So TAD communicates the design, not using views of the design. By views, I mean like not just a perspective view, but even the plan, sections, elevations. They're all orthographic projection views. So the model itself is available as a communication. That's why it's a BIM. And the representation system is infinitely recursive, and the architect can decide when to stop designing or should he continue designing. In fact, designing would never stop with something like TAD. TAD is also a desktop. It's not a drawing dependent or drawing centered. In fact, it does not have a concept of drawing at all. It can handle partial information, so you can actually talk about stuff which you know only half way through as you design, and then you flesh in the rest later on whenever you get to know about it. And then it helps retain the knowledge in your office, irrespective of people. Here are some screenshots of that version of TAD. This is an older version of TAD. 4.3 if I'm not mistaken, but it's still the same. You can I'm happy that these same models are you can use it in the newer versions also. TAD actually has been around since 1989. The first version was in DOS. I don't have many screenshots of that. I do have somewhere, but not in this particular presentation. And it can work on practically all operating systems, though it's mainly meant for Windows-based systems. But through a Wine layer, you can use it in Linux as well as on Apple machines. So this is a centerline plan which got generated in that version where it automatically processed all the information and figured out how to make the centerlines. These are some calculations which it did for FSI calculations. This is something for carpet area, this for parking. These are all done automatically. This is a very nice set of calculation which talks about various beam calculations, and this is something about FSI calculation inside. In fact, this particular part is a screenshot of one part of TAD which gives you dynamic information as you move around inside the software itself. You don't even need to invoke any application for getting this. This was one kind of a digression you can say in this presentation, which talked about something called TADSIM, which was the term which myself and Dr. J.K. Nayak, a sweet researcher from IIT Bombay, we both worked on this, where we used TAD as the underlying modeling system, and Dr. Nayak worked out energy calculation heat engine to do the balance work for this particular research project. So TADSIM, as you can see in the diagram, sits here, where it allows people to come up with climatically responsive designs. So these are all non-climatically responsive designs, and these are some kind of climatic responsive design, but it will try to push all the non-climatic designs into the climatic responsive designs. This is one slide about simulation. You can pause it and read it. It's mainly to do with what happened with that TADSIM research. We need to talk about evaluation right from early stages of design. That's what the basic objective was during that period, and then we can use it and then come up with the most satisfying alternative, which needs to be further used and further processed by the architect. You can do what if scenarios and then choose the one which is best. And then this presentation actually had a button to launch that particular TADSIM also, but nevertheless that's not what I'm going to do, because I want to really talk about TAD. This is some screenshots of actual buildings done in TAD. This is the modeling in TAD of a row house. This is the actual row house over there. I have a few more shots of that. This is the interior of that row house, and this is the interior as it looked in TAD. And again, this is one part of the interior in TAD. This is the same part as it got built. This is the model, and you can actually manipulate the model in such a way that you can actually see only the structure or only certain parts. All this is possible. This is another building. It's a large commercial project. This is the TAD model. This is the actual building. Then same thing here. This is the TAD model. This is actual building, and TAD model. So that's what it is about.